Hey y'all, welcome back. On tonight's homework, we are talking about the idea of differentiability and what it means for a function to be differentiable at a point. Number 1 says, when does a derivative fail to exist? And there are a few different cases that we've talked about where the derivative doesn't exist. For example, if you have a sharp turn in a graph, sometimes this is called a cusp. Okay, when you have something like this, an absolute value graph is kind of a classic example here. And really what you're looking for is for the slope to suddenly change. So it doesn't change gradually, but you can see like at this point right here, the slope just almost jarringly changes from being negative to positive without hitting everything in between. So yeah, if that happens and the function is not differentiable there. Other cases that exist where a derivative fails to exist would be all the different cases where we have a discontinuity. So if we have a discontinuity in a function, and that could be because we have a like a jump, maybe we've got a piecewise function that's doing something like this, or we might have a vertical asymptote, in which case the function is doing something like this, or we might just have simply a hole in the graph. But for all these three different cases, we have a discontinuity in the function. The jump and the vertical asymptote, these two are called non-removable discontinuities. And then the hole is called a removable discontinuity. Okay, so with the non-removable ones are going to be this is getting kind of cluttered in here, but the jump and the vertical asymptote, which we call an infinite discontinuity. And then the removable discontinuity is called a hole. Okay, so overall, we've got the sharp turn, we've got the discontinuities, and then the last one that we talked about was if we have a vertical tangent line. So this one's a little harder to pinpoint on a graph, but if your graph is going to do something like this and then at a point, now it just have to be at a point, but if we have that vertical tangent line, then it is not going to be differentiable also. There's a couple other corner cases that we have talked about, particularly towards the beginning of the year. One would be like a function is not going to be differentiable at its endpoints. Trying to think what else. I think that's probably about it. All right, so let's go into these specific examples and identify the intervals where the functions are differentiable and continuous. So for part A, number 2, where is the function differentiable? Well, we see that the function, really, there's nothing that we talked about up here. There's no discontinuities, there's no cusps, there's no vertical tangent lines as far as we can tell. So this is going to be differentiable on the entire interval from -3 to 2. Similarly, this is going to be continuous on the entire interval. There are no discontinuities that we can see. There's no holes, no jumps, no vertical asymptotes. So yeah, it's going to be continuous from -3 to 2. Another way to visually tell if a function is continuous on an interval is to imagine yourself trying to draw the graph with your pencil. And if you can draw the entire curve without lifting your pencil, then unless something weird's happening there, we're going to say that it's continuous. Number 3. Now here we've got, this one is not going to be differentiable everywhere. It'll be differentiable from -3 to 0, but at 0 we have a discontinuity, so it's not differentiable there. Remember that if a function is not continuous, then it is not differentiable. So yeah, we've got an interval between -3 and 0, but also between 0 and 3. The function is continuous on those same intervals. And we do have a discontinuity at x equals 0, and that would be a jump or a non-removable discontinuity. For number 4, we've got a lot of stuff going on with number 4. Where is the function differentiable? So let's highlight the places where it's not differentiable. First of all, it's not going to be differentiable at any discontinuities. So this jump at x equals 0 and this hole at what looks like, I guess we'll just call that like 1.5. Both of those discontinuities are going to prevent the differentiability. But we do see at -1, even though the function's continuous there, the function is not differentiable at a cusp or a corner or a sharp turn or however you want to call that. So we've got actually a few different intervals here. We're going to go from -2 to -1. That's going to be like this piece right here. And then it's also differentiable from -1 to 0, which would be this piece here. Then from 0 to what I'll just go ahead and call this 1.5 just to put a number down there. And then also from 1.5 to 2. As far as it being continuous, here we only have two discontinuities. We've got one at 0 and one at 1.5. So the rest of the function is going to be continuous. So from -2 to 0, and from 0 to, that's that 1.5, at least that we're estimating there. And then finally from 1.5 to 2. Okay, so those are the intervals for where it's continuous. And then as far as any discontinuities, we've got a jump at x equals 0. This is a jump or a non-removable discontinuity. And then we have one at x equals 1.5, or maybe I should, what I really should do is say approximately 1.5, because I'm not sure that that's 1.5, but that's what it looks like. And without any extra information, it's going to be a little tricky to find out what it is. I guess we could come up with that equation for that parabola, but that's not really what we want to be doing here. But anyway, we've got a hole here, and holes are removable discontinuities. So remember, a removable discontinuity is one where the limit exists at that point. Typically, we're just going to be talking about holes as being removable, and everything else, if it's a discontinuity, will be non-removable. For number 5, where is it differentiable? So you can see that it's actually continuous the whole time. There's no breaks, there's no holes, no jumps, no vertical asymptotes. So it is continuous from -2 to 2. But there are going to be 2 points where it's not differentiable, right, at these little corners here. So we're going to go from -2 to -1, from -1 to 1, and then from 1 to 2. Okay, no discontinuities. So we don't need to write them down. Number 6 says, find the equation of the line tangent to the graph at x equals 2. So this is kind of a throwback question, but we are talking about differentiability here. So first, let's find the slope. Okay, so f prime is going to be 3x squared plus 2x. And what we're trying to do is find the equation of a line tangent to the graph. Whenever we see that in our instructions, this is going to be your indication to start to set up a linear equation in point-slope form. So we need a point, we need a slope. We'll write this equation in y minus y1 equals m times x minus x1 form. So the point is going to be an x comma y, where x is 2, and then the y we'll have to find. So if x is 2, we can find f of 2 by just plugging in 2, so 2 cubed plus 2 squared. That's going to be 8 plus 4 is 12. So that's going to be the y coordinate of my point. And then to get the slope, we'll use the slope equation and evaluate that at 2. So that would be 3 times 2 squared plus 2 times 2. 2 squared is 4 times 3 is 12 plus 4 is 16. So now we're ready to write our equation. Y minus 12 equals 16 times x minus 2. Number 7 says determine if g is differentiable at x equals 0. Justify your answer. Okay, so in order for it to be differentiable, we have to check that, excuse me, that the function is continuous, and then we will check on the slopes if we need to. So if the function is not continuous, then it's not going to be differentiable. If it is continuous, that does not mean that it's for sure differentiable. Think of your absolute value function. But if it is continuous, we can check the slopes right around that point and make sure that they are equal, or at that point, I should say. So first, let's check continuity. We're going to check to see if it's continuous at x equals 0. Okay, to test that, we are going to plug in 0 into both the left and right-hand side of this piecewise function. So 3 times 0 minus 2 would be negative 2. 0 squared minus 1 would be negative 1. These are not equal. So that means we've got a piecewise function with two pieces that don't touch each other at that point. So that means that it's not going to be continuous. So if it's not continuous, that is one of those cases where the function is not going to be differentiable. So if it's not continuous, it's not differentiable. So we don't really have to go any further with this problem. We can just say no, it is not differentiable. Number 8, same kind of problem here, so we'll approach it the same way. Let's first check the continuity and check to see if this is continuous at x equals 4. That's where that break is happening between the first and second pieces. So 4 squared minus 9 times 4 minus 22 would be 16. Well, maybe I'll write this out. 16 minus 36 minus 22. 36 and 22 is 58. 58 minus 16 would be 42, so negative 42. Then let's check the next one. Negative 8 times 4 minus 10 would be negative 32 minus 10 is negative 42. So yes, it is continuous. Okay, so that doesn't give us our answer though. That is just verifying that the function is actually continuous there. And the reason why we're checking that is because if it's not continuous, we don't really need to do anything else. But if it is continuous, then we need to check on the slopes. So let's check for the differentiability. Differentiable at x equals 4. Now you might be wondering, if we have to check for the differentiability anyway, why do we need to check for the continuity? Well, because what we're doing to check the differentiability is we're going to be checking that the slopes at that point are the same. And if you have something where let's pretend you have a piecewise function that does something like this, where both of these have the same slope, then if we check if we check for differentiability only, we might run into a false positive here to say, well, yeah, the slope here is, let's just call that 1/2, and then here it's 1/2 also. Slopes are the same, so oh yeah, it's differentiable, but that is not true. Okay, this is not differentiable when you have a jump like this. Any discontinuity will prevent it from being differentiable. So we do need to check both. You can't just check the slopes. And I would recommend, since you have to check both, check the continuity first, because if it's not continuous, it's not going to be differentiable. So you can save yourself a little bit of time if you verify that it's not continuous. So anyway, let's check the value of the slope of each of those two pieces at x equals 4. So just as a little note here, the derivative of that top is going to be 2x minus 9. The derivative of the bottom is going to be, well, just negative 8. If I plug in 4 into x, I'm going to get 8 minus 9, which is negative 1, and the slope of the second piece is negative 8. So these are not equal, and therefore this is not differentiable. Number 9, and it looks like these next couple of problems are this one's going to be worked basically the same way. So let's first check for continuity. Continue. Let's just maybe word it like this. Continuous. I always have a hard time spelling that for some reason. So we want to check, is it continuous at x equals 2? Hey, it's supposed to be an x, but it looks like something else. There we go. Okay, so is it continuous at x equals 2? In order to determine that, we need to evaluate both pieces at x equals 2. make sure that they're the same. So 2 squared plus 3 times 2 minus 4 would be 4, plus 6 is 10, minus 4 is 6. Oh, not 4, 6. If we check the second piece, 7 times 2 minus 8 would be 14 minus 8, which is also 6. Okay, so these are the same. So yes, it's continuous. So now let's move on to the differentiability. Okay, to check to see if it's differentiable at x equals 2, we're going to check the value of the slopes at x equals 2 for both pieces. So the slope of the first one would be 2x plus 3. The slope of the second one is 7. So if I substitute in 2 into that first one, I get 2 times 2 is 4 plus 3 is 7. And yes, these are equal. Okay, so since those are equal, we can say yes, the function is differentiable. Okay. Number 10, determine the values of a and b, which will result in the function being differentiable. So we're going to basically set this up just like we worked the previous couple problems, except we're going to have to solve for a and b. That's kind of what we're doing. This is saying that this function should be differentiable. If it is differentiable, it's continuous. So those are going to be two conditions that we're going to have to reference in order to find a and b. Since the function is continuous at x equals 2, we can say that 2ax plus 8 equals 3bx squared plus x plus 3, basically setting the two equations equal to each other, but specifically at x equals 2. So I'm going to change all these x's to 2's. 3b times 2 squared plus 2. And yeah, so let's clean this up and see what we get. So 2 times 2 is 4. So 4a plus 8 equals 2 squared is 4 times 3 is 12. So 12b plus 6. And I guess really the only thing I could do here is maybe put this into standard form, subtract that 12b over, subtract the 8. And I could simplify this equation like a little bit. If I divide both sides by 2 here, I get 2a minus 6b equals negative 1. So that's what I'm going to go with. I don't have a, I don't have b, but I've got an equation, a linear equation that relates the a to the b. So the next thing I'm going to do is come up with another equation with a and b, since to solve for two variables, we do need two equations. But the fact that it's differentiable means that we can set the slopes equal to each other as well. So the slope of the first one is 2a, and the slope of the second one is 6b. Is that right? 2 times 3 is 6. Yeah, 6b plus 1. And 6bx. My apologies. It's like I think something's missing here. 6bx plus 1. There we go. And we want to check this at x equals 2. So I'm going to change that x to a 2. And then I'm going to rearrange this equation so it looks kind of like the one that I have over to the left. 2a minus 12b equals 1. And so look, now I've got two equations, both with a and both with b. So I can set up a system of equations now to solve for a and b. All right, so I'm going to just rewrite this system out. 2a minus 6b equals negative 1, and 2a minus 12b equals 1. You could solve this with substitution, but I'm going to solve this with elimination. I just feel like because we've got those two coefficients of 2, it might be easier to just go ahead and subtract these two equations to get the b value. So 2a minus 2a is 0. Negative 6b minus negative 12b would be the same thing as negative 6b plus 12b. So that'll be 6b. And then negative 1 minus 1 would be negative 2. So b would be negative 2 over 6, which would reduce to 1/3. So that's b. Now we got to find a. The easiest way to find a is going to be to just plug in this 1/3 into either of the two equations, kind of your pick. You could either plug it in here or plug it in here. It doesn't really matter. In fact, if you plug it into both, you can rest assured that you got the right answer if you get the same answer for both of these. And maybe I'll go ahead and do that just so you can see it. You don't necessarily have to do that, but if you're just like questioning your work, it's never a bad idea to just check your answer. So let's see, we've got 2a minus 6 times negative 1/3 equals negative 1. Or alternatively, you could have done 2a minus 12 times negative 1/3 equals positive 1. I'll solve that left equation first. 2a and then 6 divided by 3 is 2. Subtract 2 on both sides. I'm going to get negative 3. Divide both sides by 2, and I get negative 3 halves. All right, so if I get negative 3 halves over here, we're golden. If not, I guess I got to go back and find my error. So 2a plus, this would be 12 divided by 3 is 4, equals 1. Subtract the 4 on both sides, and I get negative 3. And look at that, I do get negative 3 halves. So I'm doing it right. I should have a high degree of confidence that I did everything right since I got the same a value in both equations. So yeah, a is negative 3 halves, and b is negative 1/3. Just scroll down so you can kind of see the whole enchilada there. Can't really fit everything, but you have the worksheet, so hopefully that's okay. All right, let's move on. Number 11 says determine whether the function is continuous at x equals 2. Then determine if the function is differentiable at x equals 2. Well, we'd have to check that continuity anyway, so let's just go ahead and do that. So let's check the continuity. Okay, so we need to let x equal 2 and evaluate both pieces. So e to the 2 times 2 minus 4 would be e to the 0, and e to the 0 is 1, so 1 minus 4 is negative 3. Oops. And then if I check the second piece here, x would be 2, so 2 squared minus 5 times 2 would be 4 minus 10, which would be negative 6. So this is not continuous. And the nice thing about finding that it's not continuous means that it's not differentiable also. Okay, so since f is not continuous at x equals 2, it is not differentiable there. All right, well, I think we just have one last problem. Yep, this is it. So number 12 says determine whether the function is continuous at negative 1, then determine if it's differentiable. So hopefully you're kind of getting the gist here of how we're going to approach these problems. First, we'll check the continuity. Continue. I always got to I don't know, the spelling there just really throws me off for some reason. At x equals negative 1. So let's check. Let's plug in negative 1 to both pieces. Negative 2 times negative 1 squared plus 6 would be negative 2 times 1, so that's negative 2 plus 6 is 4. And then for the second piece, we got 4 times the natural log of negative 1 plus 2 plus 4. Negative 1 plus 2 is 1, and the natural log, or really log base anything of 1, would be 0, and 0 times 4 is 0, plus 4 would be 4. So yes, f is continuous at x equals negative 1. Now let's see if it's differentiable there. Okay, so basically the same idea, but we're going to do the slopes here. So the slope of the first piece will be negative 4x, and the slope of the second piece, looks like we might have to do a little chain rule here, 4 times, actually we will not have to do technically we're going to do the chain rule, but the derivative of x plus 2 is 1, so I guess there's a times 1 here, but you don't really need to write that, and then the derivative of 4 is 0. So now we want to substitute in 1 into x to see if these two are, sorry, not 1, but negative 1, to see if these two expressions are the same. And with the first one, we got negative 4 times negative 1 is positive 4. And with the second one, we have, let's see, down here in the denominator, negative 1 plus 2 is 1. So we have 4 times 1, so this is also 4. So these are the same, okay? That means that, yes, f is differentiable at x equals negative 1. So not only is it continuous, but it's also differentiable. And so that's going to do it for tonight's homework. As always, if you have any questions or want me to go into a little bit more detail, just please reach out to me or find me in the mornings for tutoring, and I'll be happy to help you out. But otherwise, y'all have a great day, and I'll see you next time.